Okay, in today's video, I want to expand our knowledge of vectors to include something called the dot product and the projection of a vector onto another vector. So that's what we're going to focus on today. We're also going to talk about finding the angle between two vectors. So starting with the dot product of vector u and vector v is given by the same notation. Vector u dot product with vector v is equal to the first component of vector u times the first component of vector v plus the second component of vector u times the second component of vector v. And that's it. You're going to get one numerical answer when you do a dot product. You're not going to get a vector. So in this example, I'll take 4 times 2 plus 5 times 3. 4 times 2 is 8. 5 times 3 is 15. So my dot product is simply 23. When working with dot product, we also follow the properties of algebra that we've used before. So if I have u dot product of v, that's equal to v dot product of u. If I have the 0 vector times v, that's the same as 0 vector. Or if I have a scalar 0 times a vector v, it's just the 0 vector, 0. If I take u times vector v plus w, I can distribute that and do the dot product of u and v plus the dot product of u and w. If I have a vector times itself, that is equal to the magnitude squared of their vector. If I have a constant or a scalar times a dot product of u plus v, I could either distribute the scalar to the first vector and do the scalar times that vector times the dot product of v, or I can distribute the scalar to the second vector. Or I can do the dot product first, then distribute the scalar. So all three of those are equal. All right, so here we're going to figure out u dot product with 2v. So I'm going to start by multiplying each entry of v by 2, doing that scalar multiplication, and then I'm going to do the dot product, and I end up with an answer of 46. Okay, you try this. U dot product v times w. Since u dot product v is inside parentheses, I'm going to start by doing my dot product. So that's going to be 4 times 2 plus 5 times 3. And then I'm going to simplify that dot product down. I get 23 times the vector 6, 2, so that's scalar multiplication. So I'm going to take 6 times 23 to get 138, and 46 as my second entry for the vector. Number 3 is done the exact same way, except the first thing we got to do is translate the standard unit vector into component vector form. And again, I'm going to work with the parentheses first. I want to figure out the dot product of u times v, then subtract the dot product of u times u dot product with w. U dot product with v will give me negative 1 times 2 plus 3 times negative 4. And the dot product of u and w will give me negative 1 times 1 plus 3 times a negative 2. Which simplifies down to negative 7. All right, I want you to try the next one. Okay, to solve this problem, the order of operations says I need to work inside the parentheses first, and inside the parentheses, I need to do the scalar multiplication first. So I'm going to distribute the 3 into that first vector. And now I'm going to take the dot product of those two vectors inside our brackets. And last but not least, I'm going to multiply the vector negative 1, 3 by our scalar or dot product result of 30 to get negative 30 as our first entry of the vector and 90 as our second entry. Okay, next one we're going to learn is how to find the angle between two vectors. But to help us figure out or develop the formula for this, we're going to look at an example. So let's say I have vector v here and vector u, and I want to find theta, the angle between these two vectors. Well, if I write the vector above here, which is our vector v minus vector u, since the tail and end are not connected, therefore I have a triangle. And remember, to solve a triangle that's oblique, and you know two sides, or 3 sides of the triangle, you want to find the angle, you want to use the law of cosines. Since I'm looking for theta, I'm going to let a be theta. So the side opposite theta is going to be my a term. So it's going to be vector v minus vector u. And remember to find distance. Distance is the magnitude of that vector. And then I need to square that because I have a squared, is equal to the magnitude of vector u, which will be my b term, quantity squared, plus the magnitude of vector v, quantity squared, minus 2, distance of b is my magnitude of u, and the distance of c is my magnitude of vector v, cosine of theta. All right, so we're going to start by evaluating the magnitude of vector v minus u. So remember the magnitude, using that definition that we just learned, that property that we just learned, of a single vector, and vector v minus u is considered a vector, we could have called it vector w if we wanted to, is the dot product of that vector times itself. So I'm using this formula here. All right, so to figure out this dot product, we have our first term times our entry of our first term, so that's going to get us v times v, or v dot product with v, I should say, minus 2 vector v times vector dot product with u, plus dot product of u times u. And then remember, I can go back when I have a dot product of the same vectors, the same as the magnitude quantity squared. Now, if I look at the other side of our equation here, so let me go ahead and copy that down. Counting like terms, these all magnitude squares cancel each other. The negative 2 divided by negative 2 cancels it out. So I'm left with just simply the dot product of v times u is equal to the cosine of the magnitude of u times the magnitude of v. Then if I divide each side by that to get cosine by itself, end up the cosine of theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. And that is the formula that we'll be using to determine the angle between two vectors. So let's officially get this written down. So theta is going to be what we're going to represent the angle between two vectors, as long as theta has to be between 0 and 180 degrees, or in radians, it needs to be between 0 and pi. And their respective standard position vectors, so that's what the i's and j's, standard position vectors, this angle can be found by using the following dot products, And to find the angle between two vectors, you will simply use the formula cosine of theta is equal to the dot product of vector u times vector v divided by the magnitude of vector u times by the magnitude of vector v. All right, as always, it's probably going to be easier to actually figure this out if we do an example, so let me work through example 4a. So I want to find the angle between these two vectors. So I'm going to use this formula here, and so cosine of theta is going to be equal to the dot product of u and v divided by the magnitude of vector u, which is the vector 4, 3, times by the magnitude of vector v, which is the vector 3, 5. All right, so let's perform these operations. First, we're going to find the dot product of vector u times v, vector u and v. And remember to find the magnitude, that's equal to the square root of the first entry squared plus the second entry squared. Simplifying this down, I get 27 divided by 5, the square root of 34. So if cosine of theta is equal to this, theta is equal to the inverse cosine of 27 over 5, the square root of 34. And so I just punch that into my calculator. I'm going to be in degree mode. And so I get 22.17 degrees. And that'll be my answer. First thing we need to do is rewrite this into component form. Then we're going to use our angle formula. The formula to find the angle between two vectors by finding the dot product of u times v divided by the magnitude of vector u times the magnitude of vector v. Simplifying this down, we end up that the cosine of theta is equal to 8 divided by the square root of 65. So therefore theta is going to be equal to the inverse cosine of 8 over the square root of 65, which is approximately 7.13 degrees. Okay. You try this last one, but make sure you start by converting those vectors into component form. All right, now that you have it into component form, let's use our formula. Cosine of theta is equal to the dot product of u times v divided by the magnitude of vector u times by the magnitude of vector v. And now let's simplify this down until solving for theta. So in order to find theta, I'm going to figure out the arc cosine of negative square root of 2 plus square root of 6 over 4, which is 75 degrees. But our original problem was given in radians, so I cannot leave it in degrees here. So we must convert this degree measurement into radians by multiplying by pi over 180 degrees. And I end up that theta is equal to 5 pi over 12. Now we're going to look at figuring out how to prove two vectors are orthogonal, or forms right angles, or perpendicular, or if two vectors are parallel. So two vectors are considered orthogonal if and only if the dot product of the two vectors is equal to 0. Two vectors are considered parallel if and only if they are parallel to each other. So if I had vector u and vector v here, they could be parallel if they're right on top of each other, and that means that the angle between those two vectors would have to be equal to 0 degrees. And then, so since we have a formula for cosine of theta, what's the cosine of 0 degrees? Well, it's 1. So if our formula for cosine of theta equals 1, we know we have parallel vectors. Or two vectors could be parallel if they're going in opposite directions. And so that would be 180 degrees if they're put into standard position. And so that means the cosine of theta is equal to negative 1. So if the cosine of theta is equal to plus or minus 1, or more specifically, if the dot product of vector v times vector u, or vector u times vector v, divided by the magnitude of vector u times the magnitude of vector v equals either positive or negative 1, we know that our two vectors have to be parallel. So let's start with proving orthogonal. So remember, the dot product is equal to 0, then two vectors are orthogonal. So let's determine if vector u and vector v in 6a are orthogonal. So all we need to do is find the dot product of these two vectors and simplify it down. If I get any answer besides 0, they are not orthogonal. If they get 0, then it is orthogonal. So since negative 27 is not equal to 0, vector u is not orthogonal with vector v. All right, you try the next one. Again, to prove orthogonal, all I have to do is take the dot product of the two vectors and simplify it down. If I get any answer besides 0, they are not orthogonal. If I get 0, if and only if I get the answer of 0, they are orthogonal. So therefore, vector u is orthogonal with vector v in this example. Okay, next we're going to look at proving if two vectors are parallel to each other by using our formula. The dot product of the two vectors divided by the magnitude of the first vector times the magnitude of the second vector equals either a plus or minus 1. If we get any other answer besides plus 1 or minus 1, then they are not parallel. So we're going to start by finding the dot product of u and v in this example, and then the magnitude of vector u times by the magnitude of vector v, and simplifying this down to see what number I get. Since the square root of 6,084 is 78, I get 1. So therefore, I can conclude that vector u is parallel to vector v. You try the next one. Okay, start by using our dot product of vector u and vector v. Divide by the magnitude of vector u. Times by the magnitude of vector v. And then if I get anything besides 1 or negative 1, they are not parallel. All right, so that denominator is very familiar. So we know that's 78 from the last example. So negative 72 over 78 is not positive 1 and it's not negative 1. So therefore, u is not parallel to vector v. The last two things we're going to learn is we're going to learn how to find the vector components and how to find the projection of a vector. So to kind of help you do this, because most of the time we're going to use this application in word problems, we're going to go back to that boat problem that we did last video. And so we have a boat that's on a ramp, and we want to figure out, we want to look at the force applied to this. So we did it one way last time. Now another way we can do this is by doing vector decomposition, or finding the components of a given vector. In this case, the components of the force vector. So remember, force of this boat is the force of gravity, and the force of gravity is this downward motion represented by this angle here. So I'm going to call that F, which is our force of gravity, force due to gravity that pulls. Now this force due to gravity, it's not just pulling the boat straight down. Gravity is also having an impact of moving it, the force is being moved down, and also wants the force of gravity wants to make the boat roll down the ramp. So I could break up or decomposite this force of gravity into two components, and that is the force, which we'll call W1, which is that that wants to pull the boat down the ramp, and I could illustrate that here in orange as my W1 vector. So W1 wants to pull the boat down the ramp. And then we also have the force that works against the ramp, which could be this W2 here. And I'll do in blue. And so I could say the force vector here could be has W1 and W2 as component vectors. So we could say that the force vector is equal to the vector of W1 plus W2. Now notice that vector, that W1 vector and that W2 vectors are orthogonal to each other. They form right angles, so perpendicular to each other. And therefore, those two vectors, W1 and W2, are the component vectors of F. Or we could simply say that that means F is equal to the vector W1 plus the vector W2. Now, if I wanted to look at the negative of W1, so I want to go in the opposite direction, the vector in the opposite direction of W1, that would represent the force needed to keep the boat from rolling down the ramp. So you kind of want to think about that a lot of times. So a lot of these problems will ask that. What is the force needed to keep the boat from rolling down the ramp? And I think that's exactly what the last question, when we did this before, was asking for. But if they ask you for the force that's needed, the force that the tires must withstand against the ramp, then you'll be looking at, that would be vector W2. Because the vector W2 is that force pulling against the ramp. So, sorry, opposite, negative vector W2 would be represents a force that that the tires must withstand against the ramp. So some of these word problems will ask for either one. So you want to know what each component vector represents in the situation problem. All right, so now that we kind of got a basic understanding of what we're looking at, let's go do the algebra, the math here. So if u and v are non-zero vectors such that vector u is equal to, has the components w1 and w2, where w1 and w2 are orthogonal, then if I take this vector here, I could say that vector w1 is parallel to vector v, or a scalar multiple of vector v. I'll show you a picture in a moment. Then the vectors w1 and w2 are called vector components of u. They had to equal u. The vector w1 is considered the projection of u onto v, because remember w1 is parallel to a scalar multiple of v. And in our notation for that is w1 is equal to the projection of u onto v. So that's how you would write u onto v. And so the vector 2 is given by, and all I'm doing is taking that u vector from the first blank and solving it for w2 by subtracting the vector w1 from each side. So w2 is equal to vector u minus w1. Our vector v and our vector u. So here's our vector u, and let's let vector v, the base down here. And we do the vector components of vector u. So vector components would be perpendicular vectors that add up to equal vector u. So that would be, I'll call this my vector 1, and then the bottom one my vector 2. Actually, let's switch that. And notice our component vectors are always perpendicular to each other. And then vector v is on this w2 vector, a scalar multiple of it. So it could be the exact same size, it could be smaller, it could be larger, it could go in a different direction, but it's basically on the same, it's there, right there on w. So that's our vector v. So if I want to project u, the purple, onto vector v, then that's going to become our orange one down there. So that's going to be w1. So I have to label the bottom one w1 to match up my notations I did. All right, so how do we get that? Well, the formula is the projection of vector u onto vector v is equal to the dot product of vector u times vector v divided by the magnitude of vector v squared, and then all of that times by vector v. And you can research that online if you want to see where that formula came from. We just don't have the time to go through it in this video. So let's try an example. Okay, I want to find the projection of u onto v, and then I want to write u as a sum of two orthogonal vectors, one of which is a projection of u onto v. Okay, so first we're going to find w1, which is a projection of u onto v. So in order to find our projection, we're going to use our formula that we have u times v, the dot product of u times v, divided by the magnitude of v quantity squared, all of that times by vector v. So let's substitute in our information and then solve this problem. So starting by our dot product, and then our magnitude of v, quantity squared, so square and square root are going to cancel out, and then times by vector v, which is 6, 2. All right, let's simplify this down. Eight 40ths can further be simplified down to 1/5. And now do a scalar multiplication. We get that vector w is equal to 6/5 and 2/5 in component form. So that's only the first part of the answer. We found the projection of u onto v. So next we want to write u as the sum of two orthogonal vectors, one of which is vector w1 that we just found, the projection of u onto v. So remember that u is equal to w1 plus w2. And I know u and I know w1, so I need to find w2. So I'm going to solve this equation for w2. So therefore w2 is going to equal to vector u minus vector w. And so I'm just going to do operation with vectors here. We have the component form of these two vectors. And I get that our second component of vector u is equal to 9/5, comma, negative 27/5. But they didn't ask us to find that vector. They asked us to write as sum of two vectors. So I'd write vector u is equal to the vector 6/5, comma, 2/5, plus the vector 9/5, comma, negative 27/5. And you're done. All right, you try the next one. Okay, first we're going to start by finding the vector, the projection of u onto v by using our formula. So the dot product of u times v and the magnitude of v squared will end up being negative 7 over 97. And we got times that by vector v, which is 4, comma, negative 9. So our projection of u onto v would be the vector negative 68/97 and 153/97. And that answers the first question, the projection of u onto v. Now we got to find w2 and then write u as a sum of two orthogonal vectors. So we're just going to do vector operation. We take vector u minus that w1 vector we just found. Subtracting these two component vectors, we get that vector w2 is equal to negative 126,97 and negative 56,97. So therefore, if I write vector u as a sum of two orthogonal vectors, I would say vector u is equal to negative 68/97 and 153/97 minus the vector negative 126/97 minus 56/97. And you have completed this problem. Okay, I want to end today with trying to go through a word problem. I do highly suggest that you pause occasionally to help see if you can figure this out. So I would probably pause and see if you can draw a sketch of this situation. Okay, so we have a ramp that is 30 degrees, and we have a cart. And assume that the only forces to overcome is the force of gravity. So I want to draw my force of gravity that's pushing this down. Now remember, the force of gravity has two component vectors. One that is trying to push the cart down the ramp, which I'll call W1. And the one that's acting against the wheels, trying to push the wheels down onto the ramp, which will be W2. And so the force vector is composed of my vectors W1 plus W2. They're component vectors of the force vector. And let's figure out what our force vector is. So we know a 200-pound cart sets on a ramp inclined at 30 degrees. So notice our force vector there is 0, negative 200. Now, so that's the force due to gravity. Now, to find the force required to keep the cart from rolling down the ramp, we need to find the projection of F onto V. And that's going to give us our W1, the force required to roll the cart down the ramp. So that projection of force vector onto V, that's our W1. So here's our green, that's our V vector. And so we're trying to find W1, which is that red component vector, which is the projection of V onto F. Just to make life easier, we're going to make V a unit vector. And so we're going to write this. I'm going to start by writing it in trigonometric form. And so since we have the sine of 30 degrees here, we can say that W is equal to the x value of that would be cosine of 30 degrees times I, plus the y value, which would be sine of 30 degrees times j. So we can start with the trigonometric form. And then we can simplify this down to my standard vector form, because the cosine of standard position vector form, cosine of 30 degrees is square root of 3 over 2, and sine of 30 degrees is 1/2. So if I put that in component form, vector V is now the square root of 3 over 2 and 1/2. Whew, okay, so now that I found out I know my component form of vector F and vector V, I can find my projection of vector F onto vector V by using our formula. Well, first we need to find the dot product of F times V, and then divide that by the magnitude of vector V squared times by vector V. So let's do that algebra. And so our dot product ends up being simply negative 100, and our magnitude squared ends up being 1. And so we have negative 100 times our vector square root of 3 over 2, 1/2. And so if I move that back into standard unit vector form, I'd have negative 100 times by square root of 3 over 2I plus 1/2 j. So writing this in standard unit vector form, we have negative 100 times the square root of 3 over 2I plus 1/2 j. Remember, the number out front is our magnitude. So if our magnitude is negative 100, then that looks at the force required to row down the cart is a force of 100 pounds, since our unit measurement is pounds. So the force of 100 pounds is required to keep the cart from rolling down the ramp. Okay, instead of working this next example, I think we'll stop here, and then we'll work through some more application problems in class.